All right, here's a video on section 6.6 and 6.7 of the textbook, talking a little bit about Lewis electron dot structures and also electronegativity. So the electron dot structures are used for covalent compounds. So the bonding of two different nonmetals to make a covalent bond. And that means it's a shared pair of electrons. That's what a covalent bond is. If the compound has a double bond, then that means the two atoms are sharing two pairs of electrons, so 4 electrons altogether. And a triple bond is 3 shared pairs of electrons, or 6 electrons total. So before we start to bond different atoms together, we need to draw the atom itself, and that should be drawn with enough dots to represent the number of valence electrons. So in the examples below, hydrogen has 1 valence electron, chlorine has 7 valence electrons around it, and carbon, nitrogen, oxygen have the appropriate number of valence electrons for them. All right, so now that we've started with what they have, we know that they all want to have 8. So that's our octet rule. They all want to be like the noble gas elements because they all have a full set of 8 electrons in their outermost shell. So for forming a compound below, we have a few examples, or a couple of examples. The first one's CH4, methane. If we draw a carbon, it has 4 dots. And if we draw a hydrogen, it has 1 dot, just like we did on the previous slide. If we put the two of those together and have the carbon and the hydrogen share a pair of electrons, then the carbon now has 5 dots around it, if you count all 5, and the hydrogen has 2 dots around it. So hydrogen, you might have seen on the previous slide, hydrogen only needs 2 electrons to be full because hydrogen only has the first level 1s as its outermost shell. So hydrogen's outermost shell is actually filled with just 2. So that hydrogen is all set, and carbon's on its way. It's got 5 electrons, it wants 8. So if we continue to fill the other sides of the carbon with some more hydrogens and have each hydrogen bring its electron to the party, then pretty soon we have a carbon that has 8 electrons around it. And then each of these hydrogens has 2 electrons around it. So all of them are complete. They're all full the way they want to be. Instead of drawing dots, if you want to draw the shared pair of electrons as a line, that's another way it's usually drawn. The line between the carbon and the hydrogen represents that shared pair of electrons. So when the molecule gets pretty complicated with lots of dots, it's helpful to have lines instead. So the next compound shown is C2H4. If we follow a similar process to try to fill up the carbon by putting hydrogen all around it, well, first we have to put the 2 carbon next to each other because if we surround one carbon with all hydrogens and don't bond it to the carbon, then there's no way to attach that piece because hydrogen can only have 1 piece attached to it. So the 2 carbons do have to be bonded together. And then if we fill up their other sides with hydrogens, we are incomplete. We have each of the carbons, if you'll notice, having only 7 dots around it. The hydrogens are fine. Each of the hydrogens has 2, but the carbons are not complete sets of 8. However, if we move those 2 electrons in between the 2 carbons so that those carbons are now sharing 2 pairs of electrons, or 4 electrons, now that's a better situation because around each carbon we now have the 8 electrons that it wants. And then around each hydrogen we have the 2 electrons that it wants. And so those atoms are all complete. They have complete sets of electrons. And then if we want to redraw the compound with lines instead of dots, then that's how it looks with the carbon-carbons having a double bond. So this takes a little bit of practice. There's a lot of more examples in your textbook and some different problems to try. Just when you're going over the problems, this chart can maybe help keep in mind what you're supposed to be going for. Hydrogen, of course, will only be able to have 1 bond and no lone pairs. It only has the 1 valence electrons. It's going to form 1 bond. Once it has a shared pairs of electrons, it's done and it's full. The carbon, as we saw in the previous slide, has 4 valence electrons, so it will form 4 bonds to get its 8 electrons. It does not have any lone pairs, has 0 lone pairs on carbon. Nitrogen has 5 valence electrons, and so if you draw the nitrogen again, you'll see that it looks like it has space for 3 things to attach to it, and that is correct. It will form 3 bonds, and then it will have a lone pair, a pair of electrons that is just sitting on the nitrogen, not being shared with anybody. Oxygen and sulfur each have 6 valence electrons, so they form 2 bonds, or either one, oxygen or sulfur will act this way. The oxygen will form 2 bonds, and then there will be 2 lone pairs left on the oxygen. So those are electrons that the oxygen sort of owns. It's not sharing with anybody. Then any of the halogens, fluorine, chlorine, bromine, iodine, they all have 7 valence electrons, and so they're almost full. They just need to have 8, and so in order to fill them up, they just need to have 1 bond, 1 shared pair of electrons. And then it has 3 lone pairs on it to fill up the rest of the 8. All right, so section 6.7 is actually where your book talks about electronegativity. We also mentioned it in class. It's a measure of how strongly an element is going to hold on to the electrons that it's supposed to be sharing. So if an element has higher electronegativity, it's going to be holding onto its electrons more tightly. And so if 2 elements are sharing electrons, we can look at the difference in their electronegativities and see how evenly that sharing is going to occur. And we're not going to have to memorize the electronegativity values. If you need those for a problem, they'll be provided. If you're doing a problem in the textbook, there's a chart there for you to look at. So if the 2 atoms that are combining have a difference in electronegativity of less than 0.45, so it's a pretty small difference, then the sharing between those atoms will be fairly equal, and that is called a nonpolar covalent bond. So covalent bond is a shared pair of electrons, and nonpolar means it's fairly evenly shared. There's not a negative and positive end. If the difference is bigger, then the sharing taking place is unequal. There's a polar covalent bond. One of the atoms is going to be grabbing those electrons more than the other, and there will be a negative side to the bond and a positive side to the bond. So that's why it's polar. And if there is a huge electronegativity difference, meaning more than 1.8, then there's not really sharing taking place at all. That one atom will just transfer electrons to the other, and then that atom that has lost the electrons will be positive, the one that has taken the electrons will be negative, and you have an ionic bond. And there's an example down below. Carbon has an electronegativity of 2.5, and oxygen has 3.5 electronegativity. The difference between those 2 numbers is 1.0, and that would make it a polar covalent bond because it's between 0.45 and 1.8. And so since oxygen is more electronegative, it's really grabbing onto the electrons more of the time. The oxygen is more negatively charged, and the carbon is a little bit slightly positively charged because it's missing out on some of the electrons.